My name is Ola Hammarsten. I'm a professor and chief physician at Clinical Chemistry at Sahlgrenska University Hospital, Sweden. In this movie, I will explore the math behind extracellular clearance between cells. The biological details of this system is described in two separate movies. The starting point is that troponin is constantly released by cell wounds, and the same cell can reuptake troponin by endocytosis. Release and uptake is therefore expected to be directly proportional to the membrane surface. However, the uptake is dependent on surrounding extracellular volume. Large extracellular volume results in fewer troponin molecules per unit volume, and hence it takes longer for each troponin molecule to bind a scavenger receptor. I will now explore how extracellular clearance between cells, or cleaning your own backyard, will behave in a simplified tissue section with cubic cells. Let's assume that we have a cubic cardiomyocyte with a length A and a membrane surface of 6A squared. The cubic cell resides in a cubic changer with the size 3A, and hence the volume of 3A cubed. If we only want to explore the relation between membrane surface and surrounding extracellular volume, we can simplify by letting A be equal to 1, and we get the relation 0.22. Unit extracellular volume is roughly 5 times larger than a unit membrane surface area. With this relation, most troponin that leak from the cubic cardiomyocyte will not bump into any scavenger receptor on the surface, and most troponin molecules are not taken up by endocytosis. Let's put the cubic cardiomyocyte in a smaller cubic chamber. In this case, the unit membrane surface is 2.7 times larger than the unit extracellular volume. Therefore, most troponin molecules that leak will bump into scavenger receptors on the cubic cardiomyocyte. Most troponin molecules are therefore reabsorbed, resulting in a lower steady-state level of troponin around this cell. We can easily imagine the two cardiomyocytes will leak twice the amount of troponin if far apart. But if they are moved in proximity to each other with a distance x, some of the troponin will be endocytosed by the peer and limit the steady-state level of troponin around these two cells. To explore the math further, I will use a simplified tissue model with 27 cubic cells forming a cube of tissue where the extracellular volume is the sum of all volume between the cubes. Extracellular volume is dictated by the distance x. If cells are far apart, extracellular volume is large, and if moved more close, extracellular volume, the sum of all volumes between the cubes, are smaller. However, the total membrane surface of the 27 cubes remains unchanged in this model. We now build the mathematical description of the extracellular volume of the tissue. The cube of cubes will have a volume of the expression shown. The 27 cubic cells will have the volume of 27 times A cubed. Therefore, extracellular volume will be the difference between these two expressions. If we divide the total membrane surface area, 27 times 6A squared, with extracellular volume, we have an expression for the relation between unit membrane surface and unit extracellular volume. As we have seen, when a lot of membrane is confined to a small volume, extracellular clearance is expected to become more efficient. But how much more efficient? Our expression can be simplified by the relation between cell length A and the distance between cells x, that we call Z. That is, the distance between cells described in the number of cell diameters. We substitute x with this expression. Finally, we remove the cell length A by assuming it to be 1. After all, we are interested in a relation, and hence the actual value of A and x is not important. Finally, we're left with an expression that only have one variable, z, distance between cells, described in the number of cell diameters. The plot shows a nonlinear relationship between z and the membrane surface per extracellular volume. When the value on the y-axis is high, we expect that extracellular clearance would be efficient. When the value on the y-axis is high, there will be a lot of unit membrane surface per unit extracellular volume, and the troponin molecules often will be caught by the scavenger receptors. If the distance between cells is 80% of the cell size, that is, a Z of 0.8. The unit membrane surface per unit extracellular volume is 2.3, whereas if the distance between cells are 24% of the cell size, the membrane per extracellular volume is 10.9. In this part of the curve, if one changes the distance between cells, not much happens to the membrane per unit extracellular volume. That is, the efficiency of extracellular clearance does not change very much if cells are separated 80% or 24% of the cell diameter. With this mathematical expression, we can now examine the real case, heart tissue. It is easy to see that the distance between cells is roughly 5% of the cell diameter of red cardiomyocytes, a Z of 0.05. When Z is 0.05, we are placed on the exponential part of the curve. Even the smallest change in distance between cells result in a large change in the relation between unit membrane surface and unit extracellular volume. That is, if cells are separated by a local edema, the expected efficiency of the local clearance of troponin will drop exponentially and possibly result in a reciprocal increase of stable troponin levels in the circulation.